Hello, everybody. Welcome back to the fifth and last part of the income distribution series. In this series, I used Swiss income data given in terms of a relative frequency table to show how to calculate certain values from this data. In the first part, I calculated the histogram, cumulative relative frequency table, and ogive. And in the second and third part, I calculated mean and median of grouped data. In the fourth part, I calculated Robin Hood index, index used for inequality as inequality measure. And in this final part, we will calculate Lorenz curve and Gini index. Okay, so let's look into our data again. So let me remind you what these columns all mean. These are the different classes of monthly income. So this is a class of our population which makes between 4,000 and 5,000 francs per month, and they are 25.8% of the population. And so this was a relative frequency table, our starting point. Now what we want to calculate is the Lorenz curve, and you should remember what the Lorenz curve values indicate. The Lorenz curve tells you how much of the whole cake uh, is going to the poorest 10%, the poorest 20%, the poorest 50%. So, for instance, a value of the Lorenz curve could say that the poorest 40% of the population get 20% of the whole cake. And because we are talking about always the poorest 10%, 20%, whatever, this clearly indicates we need to use a cumulative relative frequency table, which is done below, because these classes here, the people who are making less than 1,000, less or equal 2,000, less or equal 3,000, are exactly these classes we talk about when we talk about Lorenz curve. So this cumulative class is the poorest 0.2% of the population. This one is the poorest 0.6% of the population. This one is the poorest 2.3% of the population, and so on. So these values are the x values of our Lorenz curve. So all we need to know in order to be able to draw the Lorenz curve is how much of the whole cake goes to the poorest 0.2%, how much of the whole cake goes to the poorest 0.6%, and so on. So we need some percentages here. We want to put them here, so we call it the relative amount. So the relative amount of the whole cake going to these cumulative classes. And that's what we want to have. And then, of course, these values in these two columns would be the points of the Lorenz curve. Now, in principle, we could do this immediately, but I still want to use the same approach which I have used in video number 4 when we talked about Robin Hood index, because then we go about absolute amounts. And this is a little easier to conceptualize, I suppose, talking about absolute amounts first and then going from absolute amounts to relative amounts. So I want to have another column here, which are the amounts. So how much do the poorest 0.2% of the population get? How much money, not of the whole, but how much money absolutely do the poorest 0.6% of the population get? This would go here. So keep in mind, our approach was that we assumed that we have 1,000 people, only 1,000 people, which of course is not realistic. But this doesn't matter, because the result will always be the same no matter what you assume. But assuming a certain number makes thinking about these concepts a little easier, I would say. So keep in mind, if we have 1,000 people, then we can go into these classes here, the non-cumulative classes, and calculate the frequency. So how many people are getting 0 to 1,000? If 0.2% of the population get between 0 and 1,000, and we have 1,000 people, then the frequency, the amount of people in this class, is certainly then the relative frequency multiplied by the total amount. And remember, this absolute referencing we did in video number 4 with the dollar signs. So it's $1 because we want this F1 reference be fixed throughout. Then, of course, the amount is easy to calculate as well if we have the frequencies of these classes. The amount in this class here is 500 times 2. Well, it's not exactly 2, it's 2 point something, so it's about 2.2. And the same here. So the amount is always the number of people in the class multiplied by the midpoint, because the midpoint of the class would be the average income of people in this class. It's our assumption throughout. So we know how much the people in these different classes get together. And now we are looking not at the classes, at these classes, but we look at the cumulative classes. And remember, the first cumulative class is exactly the first class here. So 0 to 1000 is the same as less or equal 1000. So this amount can be copied immediately. We can just say this one is equal to the 1010 we have here. And the total amount of the second class is the sum of the amounts of the first two classes. So it's this one plus this one. So we can do it this way if you want to. And the third one would be the sum of the first three classes. So it's this one plus this one plus this one. And of course, we could go on and it gets a little messy to get all these plus in. Of course, we could use AutoSum to simplify things a little. But the best way to go and do these calculations is the same way we did when we calculated the cumulative relative frequency table. Remember, in video number 1, we are saying the amount of the total amount of the class less or equal 4,000 is the same as for the class less or equal 3,000. So what we have so far, we extend these classes step by step. So we go to the previous cumulative class and say, okay, this was a previous one. So it's 50,000. And then we add what the people between 3,000 and 4,000 bring. So we have everything up to 3,000 in the cumulative class, and we add this amount here between 3,000 and 4,000. So this formula is very good because it allows us to drag it down, to copy it, and to fill out all these formulas without doing the calculations one by one. But of course, there's nothing wrong with doing it one by one. Just takes much more time. So let me just check whether I got the right row here, 3,000 to 4,000. Yes, that's exactly what we want to have. So we have the previous one plus the F7, and then I'm getting this one and dragging it down all the way. And yeah, by the way, this one, no, it doesn't really matter. It doesn't affect us yet, but eventually we need to move this to the right. So maybe we should do it already. I'm highlighting the whole block. I'm using Control X. Well, I'm highlighting the whole block. I'm using Control X for copying, and I'm pasting it maybe here, where it does not bother us much. So this median stuff from video 3, we move away. What do we have here? 6 million francs. And actually, we should drag it one more down. So 6.2 million francs is what all people together make. And you see this, of course, matches with this number here, 6.2 million. So the sum of all these amounts in the original classes is the same as the sum of the amount, the total amount of the all people. And then what we need to do is only, we need one more round for relative amounts. And what is a relative amount? It's how much the cumulative class gets and divided by the whole amount. And the whole amount, again, I can either grab from here, or I can grab it from here. Doesn't really matter much. Um, which one do I choose? Maybe I take this one here. Keep in mind, I need the dollar sign again in front of the 49, because if I drag down this formula, again, this absolute referencing, which was mentioned in video number 4, if I drag down this formula, it should always be divided by D49, because there's nothing below D49. You see, well, other stuff, but nothing relevant for our case. But the D29, of course, should move into D30, D31 if you drag it down. And this one, maybe we want to format into percentages first, and then maybe we want to show 1 digit. And it's a 0.0. It's not exactly 0.0, it's 0.0 and a little, but I want to show only 1 decimal. So let's say it's almost nothing. I drag it down and let's see. And here we go. So the poorest 14.3% of the population get 70.6% of the cake. So always less than what they are, of course, because they are poor. The poorest 40% get 26% of the cake, and so on. So these values in these 2 columns are our Lorenz curve values. And in principle, I would also like to have 0, 0 at the starting point, but maybe it is not necessary. I don't really have space for this, so maybe we can go without. So I'm highlighting these 2 columns, and I want to graph them. But the graph is a different one than the one in the histogram and in the ogive, because the x values are not spaced uniformly. They are spaced in a very strange way, as you can see. And of course, this is also the difference if you do Lorenz curve coming from quintiles data or from deciles data. Then you have x values which are equally spaced. And in this case, you don't. So we need a different graph here. Again, we need to insert a graph. So I'm going to insert, and I'm going to the graph section. And what I want to insert is a so-called scatter plot or scatter chart. Excel calls it scatter chart. A scatter chart just plots these points, x and y coordinates. So these are 20 points we have with x and y coordinates, and it plots these points in the Cartesian coordinate system. And if I click on this one, you see I have different options: just the points, or the points connected by a curved line, which actually looks rather nice, or the points connected by straight lines. This one actually looks even nicer and maybe more realistic. But this one is essentially the Lorenz curve we will deal with, because we are assuming that between each of these 2 points we have a linear graph. This is not really realistic. This one is a more realistic one, but this one is our model. So we have a little difference, as you can maybe not see. It looks almost the same, but there is a slight difference here. Still, I want to show it with straight lines. Again, up to you what you do. But I do it this way. I click it in, and I call it the Lorenz curve because it's a Lorenz curve. Well, let me try. Okay, Lorenz curve. I try to make it quadratic because a Lorenz curve looks quadratic, and you see the x and the y axis go from 0 to 120%. For some reason, Excel gives a little space. If you don't like this, you can change it, but I really don't bother. So for me, this is my Lorenz curve. And again, keep in mind, my square is essentially going around here. So changing this again is easy. You must just format the axis, but I think that's all right. So here's first step of our approach, the Lorenz curve of our data. Okay, next let's calculate the Gini index. And remember, the Gini index is twice the area between the diagonal, this is the diagonal here, and the Lorenz curve. So we look at the area between diagonal and Lorenz curve, and we multiply it by 2 to get the Gini index. And in order to get this area between these diagonal and Lorenz curve, we need to find the areas of these trapezoids. So remember, trapezoids means we look at two consecutive points here. We go down to the x-axis, and this part here. And trapezoids has a very easy formula. It's width times average height. And the average height is left height, right height divided by 2. So that's what we do. We calculate the areas of all these different trapezoids we have, and we calculate it in this table here. So we make a column for the areas, and then we add these areas to get the total area below the Lorenz curve, and then the area between diagonal and Lorenz curve is 0.5 minus area below, because the area below the diagonal has an area of is 0.5. So that's what we do. And keep in mind, the first shape is not a trapezoid, really. Strictly speaking, it's a triangle. And the triangle has a width of 0.2 and a height of 0. Well, looks like 0.0, but it's not. It's a little larger than 0. So, but this is the height of it. And remember the triangle formula, it's width times height over 2. So the first one is a triangle formula. We are doing width times height divided by 2. And it looks like nothing. Again, this is scientific notation. So it's a very, very small number because it's a very, very small triangle. So we don't really care much about this one. Next one is a trapezoid. And the width of this trapezoid is a difference between these two values, because we have the first point on the Lorenz curve and the second one, 0.2%, 0.6%, and the distance, of course, is a difference between both. So the formula here would be width of the trapezoid, which is, and I have to use parentheses here again, it's this one minus that one. So the large one minus the smaller one. This is my width. And I multiply it by the average height. And remember what the average height is? It's the left y value plus the right y value divided by 2. So we need parentheses here. We take the left y value, which is not exactly 0, it's 0 point something, plus the right value divided by 2. This is my trapezoid formula. And keep in mind that here the formula is different than it was in the case of quintiles and deciles, where we would always have a fixed base. Quintiles 20%, deciles 10%. So it's not. We have to calculate the width of these trapezoids because different trapezoids have different widths. So it gets a little more complicated. What do we get? Another very small number. And again, I can now copy this formula down all the way. So this is the last one we have. And you see all these values are small, but not as small as the first ones. You see, of course, they're all smaller than 1, obviously, smaller than 0.5, obviously. But not all of them are really totally small. And what we need is to get the sum of these areas. So here, again, an autosum, I'll be going here. I click in the autosum. Excel understands that I want to add all these areas of the trapezoids and the one starting area of the triangle. So let's see what we get. We get 0.38. So 0.38 is the area under the Lorenz curve. And the area under the diagonal is 0.5. That means between diagonal and Lorenz curve, we have the difference between these two values as an area. So the area between the two curves, diagonal and Lorenz curve, is 0.5 minus 0.38. So let me maybe write this here. We're looking at the difference between, and maybe I'll use already parentheses because I need it in a second. So we are subtracting This one should be equal sign here. We're subtracting this value from 0.5. This is the area between diagonal and Lorenz curve, but keep in mind Gini index is twice the area between diagonal and Lorenz curve. So we are not dividing, we are multiplying by 2. So Gini index is twice the area between these two curves, which is twice times 0.5 minus the area below the Lorenz curve. And here it is. Here's my Gini index. I want it as a percentage, and I want to have it with 1 decimal maybe. This is my Gini index. So let me write it down, Gini index. And I want to color it again because it's one of these main results. So the Gini index of the female full-time employees in Switzerland is 22.5%. Now you might wonder, why is it so small? Gini index in Switzerland is about 32%, maybe 33%, around this. Why would this number be so small? Did we make a mistake? Think about it for a second. There's not just one Gini index in Switzerland. It all depends on what the population is. So we could look at family income in Switzerland. We could look at household income. We could maybe look at individual income, even though this is a little more difficult to calculate. How do you deal with children? And here we are looking only at female full-time employees. So of course, many people who are really poorer than these people we look at are not part of the equation. Let me show you one more thing. Remember, we assumed 1,000 people, and I told you now repeatedly that this assumption is not really necessary. So look at the two data we calculated. We looked at Robin Hood index in part 4 and got 16.1%. And for the Gini index, we got 22.5%. Now assume we don't have 1,000 people, but maybe 10,000 people. How do these two values change? And you see, if I release it, a lot of things in the sheet will change. All these numbers here will change, as you can see. But the Robin Hood index is still the 16.1%, and the Gini index is still our 22.5%. So both of these calculations are not depending on the assumption on how many people we are looking at. Thanks for watching. Bye-bye.